0 just from this equation alone. This is node 2. Okay? And then V1 is 0. You plug it back into the first equation with V1 being 0. You get a simplified first equation. You get minus Vt over J2 is equal to J. Okay, that's what becomes of equation 1.
Plus 1.
What is that? This is correct, right? If set V1 to 0, I get this equation. It's correct, right? So Vt must be equal to, if you take this over to the other side, is 1 minus J times J2. Okay, which is equal to 2 into 1 plus J. Right? So that is the answer. I got it correct. Both. Okay? So V7 is just found to be that quantity over there. Any questions regarding this? And then example 418 is very similar to this example, but you're asked to find the short circuit current at the output there. So you're going to put a short. So you're going to put the short over there. I'm going not to redraw this figure. Is that okay? I'm just going to use back the same figure and just put a short circuit here. And you're asked to find what IN should be. Okay? And you're asked to find what IN should be by using the loop current method. The first method that we have done is the node voltage method that you're very familiar with for resistive networks. Now you apply the loop current method. So let's call this loop to have current I1, and then this loop to have current IN. Okay? And this loop, it's quite clear that this current here would be just equal to J, I1 plus J, right? I1.
Yes and no. Will it just like I1 plus J would just be the current going through the inductor?
Yeah, I1 plus J is a current going through the inductor, that's right. So this current will be I1 plus J. Okay, you have this providing J amperes. So if you look at the current through here, it will be I1 plus J because this is an open circuit to this current I1. Okay, a current source will appear to be like a open circuit. So this current cannot go through here. So the current that goes through this arm has to be equal to I1, which is coming down here, plus J. So this current must be I1 plus J by Kirchhoff's current law. Okay? So this loop must have a current of I1 plus J. And sometimes you call this a super loop. Okay, but don't worry about that. Okay, they call them super loop and super nodes, but don't worry about those things. Okay? So this current is just I1 plus J, and then this current, you can figure out what the current through the capacitor should be. Okay, then you write the Kirchhoff voltage law for this big loop. Okay, for this big loop, which is called a super loop. So if I were to write the Kirchhoff voltage law for loop 1, let me do it for loop 1 first. That is in accordance to plus J2. So I have two volts. Okay, I have 2 volts coming from here. 2 plus the voltage drop across this thing, it will be J2 times the current through it. The current through it is I1 plus J. Okay? So this, I'm actually writing down Kirchhoff voltage law for this big loop. Okay? And then I have to figure out what current goes through the capacitor. The current that goes through the capacitor is the difference of these two currents. Okay? And then the impedance of the capacitor is minus J2. The difference of that two currents is I1 plus J minus IN. Okay, this is the current through here. So if I were to draw this current, this is I1 plus J minus IN. Okay, this is that current that goes down that thing. Okay, and that times the impedance is the voltage drop over there. Okay, and then finally I have to put in this voltage. I've not accounted for that voltage drop yet. So I will have to have 2I1, and adding them together give me 0. Okay, so this is the current loop method. The loop 1 is this big loop over here. Okay, that is the big loop over there. Then loop 2, I will have to say that IN, which is this loop over here, okay? Let me call this loop 2. And that big loop, loop 1, and this is loop 2. Let me call this 2. Okay, so I have IN minus J 2 times the current that flows through that. The current that flows through that is the opposite of this current. Now, if I'm going this direction, that current is just the negative of that. So I have J2 times IN minus I1 plus J. And that must add up to 0. So I have loop 1, loop 2. And then you are supposed to simplify. 2 equations, 2 unknowns, and you simplify. Okay? You want me to simplify them? No? It's a lot of work, right? You better pray that it's not on your exam. So lots of algebra. So you try to look for things that cancel each other. You can see that these two terms cancel each other, I think. Some of the things cancel each other. This J2I and this J2I cancel each other. And then the first equation would just have I1 equals to minus 1 minus J IN. Okay, that is equation 1 becomes something like that. Equation 2, you can simplify too, and then you solve for IN. Okay, IN is rather complicated looking. Okay, the final solution for IN is a ratio of 2 complex numbers. But if you have your skill all up your sleeves, then you know how to do them. Okay. So if you have acquired a whole bunch of skills or tricks up your sleeve, then this is your IN. Okay. I won't work through the details. Any questions as to how you can do complex algebra and then complex arithmetics? I'm sure that all of you know how to do that at home, how to do this at home. Okay. Okay. So let's do the last example before the bell rings. So you're asked to find the Thevenin equivalence of this thing after having worked things out, okay? So you know the short circuit current, you know the open circuit voltage, which we found just now. Where did we find it? We found it to be this. This is the open circuit. And then the open circuit voltage is equal to 2 plus J2, which is D Thevenin. I Norton is I short circuit, which is that very complicated quantity over there. And then R, the Z Thevenin will be just the ratio of the two. And voila, it simplifies, right? Vt divided by In, what do you get? What is that? 3 minus J2. Okay? 3 minus J2 ohms. Okay? That is the last example. So I have a few more minutes, so you can ask any questions that you like. Oh, don't ask that question. Okay. But maybe I just spend the last 2 minutes telling you what an inductor and what a capacitor is. So if you look at the impedance of an inductor, and if you look at its magnitude, it is this one. So if you plot things as frequency of an inductor, it goes like that. The impedance increases as the frequency increases, which means that it's harder and harder to send a current through an inductor as the frequency increases. So inductors are also called frequency choke. I don't know if you've heard of this term. They can be used to prevent high frequency currents from going through an impedance. Okay, if you look at that for the capacitor, it's just the opposite. If you look at this thing, it's 1 over omega c. So if you plot this quantity as a function of thing, it goes like that. The higher the frequency, the lower the impedance that it has. Okay? So a capacitor is also a bandpass filter, a high-pass filter for high frequencies, which means that high frequencies can go through capacitors very easily. Okay, but it's a low-frequency choke. It prevents low-frequency current from going through a capacitor. Okay. So why do they have this property? Well, if you think of a capacitor, it's a charging and discharging device. So if you are going to pass high frequency signal through it, it charges and discharges. And it appears like a short circuit all the time. Remember in the beginning, before you charge up a capacitor, it appears like a short circuit. So if you charge it with high frequencies, you never have a chance to charge up. So it appears to be a short circuit at very high frequencies. Okay? And at low frequencies, you can charge up the capacitor and turn it into an open circuit. So it has very high impedance. But an inductor is just the opposite. It is something that resists sending current through. If you try to send a current through an inductor with the voltage, it resists currents from going through. Okay? So as the frequency gets higher, it's harder and harder to send currents through the inductor because there will be Lenz's law pushing back at you. And hence you have this kind of behavior. Okay? Just 2 minutes about inductors and capacitors.